it could either desorb. We've already written that down. We don't have to write it down again. It can break its carbon-carbon bond. What other bond does it have to break? A hydrogen bond. How many hydrogens are in ethane? So do we have 6 different hydrogen bond activations? Symmetry means that we only have 1. No, I mean, you can only break 1 at a time. These are all elementary steps, so we can only break 1 thing at a time. So we have C2H5, and I'll help you out. That takes up 1 site, and I make a hydrogen. All right, let me give you another piece of data. If I run instead of this, if I run this species, methyl cyclohexane. If I run this, again with hydrogen, and I'm trying to break it apart to make, I'm just ring opening. I'm not actually breaking the molecule, but I'm still breaking a carbon-carbon bond, and I'm making N-heptane. So there's 7 carbons here, so I'm just ring opening that species. I observe equilibrium between methyl cyclohexane and toluene. So for that alkane, for that cycloalkane, I know that I can easily break and remake carbon-hydrogen bonds. And that's how I form an equilibrium between methyl cyclohexane and toluene. Yeah?
So you're suggesting we remove the hydrogen, we separate out a hydrogen like that, then we separate out another hydrogen, then we break the carbons, and then...
So what's the next step? You're on the right track. All right, so let's remove another hydrogen. How many hydrogens does an ethyl have? That's what this is. This is ethyl. It looks like this on a surface. There's a CH2 here. There's a CH3 here. How many hydrogens does it have? 5. How many are symmetrically unique from one another? 2. So let's write them both down. I can either remove the hydrogen from the methyl, and that makes ethylene, which we talked about a little bit last class. And then we need a hydrogen. So that means that I need some sites over here. We want to balance our sites, so we actually need 2 sites in order to do that reaction. 1 second. Let me go ahead and put up this other one. Or I can remove a hydrogen from the CH2, so the one that's already bound to the surface. I can remove yet another hydrogen from that carbon, and I get this. And so I need slightly fewer sites here.
Do you still need an extra site to so that the carbon wouldn't be deficient of electrons?
I know what you mean, but sites are not bonds to the surface.
And if we're doing this with that, with the stabilization, does it have to be chemisorbed and not physisorbed, as was suggested earlier?
This is physisorbed. Everything else that you're looking up here is chemisorbed. The only thing that's physisorbed is ethane. Everything else, we've broken it apart, and so it's forming chemical bonds to the surface. But don't get confused. Chemical bonds to the surface are not the same thing as sites. If I have CH, it forms 3 bonds to the surface, and it still only occupies 1 site. Yeah?
So this mechanism suggests that ethane is large enough that it can physisorb, but subtracting 1 hydrogen makes it small enough that now it's going to chemisorb.
Well, I'm making a radical if I don't. I'm removing something from the molecule. It can't go back into the gas phase as a radical. I mean, it can, but it really, really doesn't want to. Yeah?
What does the picture look like for the line where it's C8 or C2H6 double star going to that line? Yeah. What is
you want to know what this looks like?
Yeah, the picture.
That's this guy.
Yeah, but that's the product. What is the react?
Looks like this.
But it takes
It's
up
physisorb.
it's taking up 2 sides.
Yeah, it just means that there's an area which it occupies.
Okay.
But it doesn't mean that it has to be chemi-absorbed. Remember, sites are not adsorptions to the surface. And really, I could have done this as a dissociative adsorption too. Nothing changes, right? I mean, take my word for it, nothing changes. All right, can I cleave the CC bond in ethyl? If we're just writing down possible reactions, then yeah, we'll include that one too. I need to react with a site here, and I make CH3 plus CH2. All right, but let's come back to our hint over here. So we observe that there's an equilibrium between benzene and toluene. So that might suggest that if I have ethane, there might be an equilibrium between ethane and ethylene. The problem is I don't observe one. And the reason that I don't observe one is because this data is at very high hydrogen pressures. And at high hydrogen pressures, the equilibrium concentration of ethylene is extremely small because the equilibrium pressure of ethylene is equal to the pressure of, ethylene is equal to the pressure of ethane divided by the pressure of ethene, and then of course I have a rate constant somewhere. K is equal to F. So I have some equilibrium constant, and then as I go to higher and higher and higher hydrogen pressures, the equilibrium amount of ethylene gets smaller and smaller and smaller. And in fact, in this case, it gets so small that I can't detect it using a GC in this case, but it doesn't matter. You can't see it. So if it's there, we don't know. So it's just a guess that we have that this may be equilibrated. Meaning that I could write this as reversible. By inference, I could also assume that that's equilibrated. This one would also have to be equilibrated because, again, I'm having an equilibrium between ethane and ethylene. So both of these have to be equilibrated. Quasi-equilibrated reaction, I'm going to put a circle on. Reversible reactions don't get a circle. I'm also going to assume, out of convention and because I know it's right, that ethane and hydrogen adsorption-desorption is also quasi-equilibrated. Again, quasi-equilibrated just means that I can go back and forth with this reaction many more times than I can do what would be a difficult reaction, such as breaking the carbon-carbon bond in ethane. This is equilibrated, and this one's not. So I'm going to leave the carbon-carbon bond activations as irreversible steps. Okay, so let's take and let's derive quickly a rate equation if we assume that this step, carbon-carbon bond cleavage of ethane, is the rate determining step. And let's just see what we get. So we start with the rate. It's equal to some rate constant times what? The concentration of adsorbed ethylene. That's it. It's an irreversible reaction. I stop there. Of course, if I were doing this more thoroughly, I would have given this reaction a number and put a number on the rate constant. But just don't worry too much about the rate constant. And then what is C2H6? If its adsorption is quasi-equilibrated, what can I write for its concentration term? The equilibrium constant, and I'm just going to put C2H6 to let you know it's for that adsorption, times what? Yeah, we'll go ahead and put pressure in there. Pressure of C2H6 times vacant sites squared. And so again, what do I get? I get K times now a big K, C2H6. The pressure of C2H6. And then vacancy squared. I'm going to give you a little bit more help that we have from the experimental data. I'm not going to explain how we know this is true. You can ask me later if you're really curious. What is our site balance? What's on my surface? Empty sites, correct? Let's skip that for a second. What else is on my surface that doesn't have a carbon in it? Chemisorb hydrogen atoms, not molecules, right? Dissociative adsorption. We don't have a physisorb dihydrogen. It just breaks apart. And then I have a zoo of things that have some carbon, some hydrogen, maybe just carbon, right? There's a bunch. I can make a whole crap load of these species. I think it's 20 different carbonaceous species are derived from ethane. I will let you know that the coverage of hydrogen is approximately equal to 1 at the conditions of the experiment. So, I've given us some more information. Our starting point is a hydrogen-covered surface. So what can I use for star then? For the concentration of star? No, you're thinking of the coverage. So let's look at this equation. What is the quasi-equilibrated reaction here? So what is the equilibrium constant for this reaction? KH2. What is that equal to?
Star squared.
H star squared